Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yes, actually what I'm going to tell you about today is how we solved the problem of bogus overlapping warnings GADT used to issue for the past 8 years. We've been working on this with Professor Thomas Revers and Dimitris Vitiniotis, Simon Peyton-Jones, and Nikolaos Papaspirou from Greece. So let's start with the basics. Well, functional programming languages like Haskell or ML, they use algebraic data types to structure their data. A typical example is a list. As you can see here, when we define a list, we represent its list. Every list may either be an empty list or the concatenation of a head and the tail of a list, which is represented with constructors nil and cons respectively. Once we have declared the data type, the only way to construct values of this type is by using the constructors alone. Like for example here, L is a list containing integers 1, 2, and 3, and is created only using constructors cons and nil. Now, once we have the data, what can we do with it? Well, the main way we have in functional languages to inspect and extract information from a term created by constructors is by pattern matching. For example, foo here takes as arguments two lists, and depending on the structure of these two lists, either returns 1, 2, and 3. Well, through the example, for example, here we call foo. On these two lists, as you can see, the arguments both can match the first clause, so GHC returns us a 1. While if we call it with these arguments, you can see that although the first argument can match the first pattern of the first clause, the second one is an empty list, so it cannot match the first. So we try to match the second clause. A wildcard represents a don't care value, so we ignore the first argument. The second argument is a nil, so we match and we return a 2. What I wanted to show here is that Haskell's pattern matching always performs top-down and from left to right. In this sense, we always try to check to match against the first clause first, and always do this from left to right. If we fail, then we try the second one, etc., etc. Right? Well, what will happen in this case? As you can see here, the first argument is an empty list, and the second one is not, and none of the clauses we have for foo can actually be matched with these arguments. So we get a runtime error. Well, that's not what we would like to have from a statically typed language like Haskell, where we want some guarantees from our type system. And in this case, we want to know that if a term is well typed, for example, that's called to foo there, if a term is well typed, then we don't expect to have a runtime error. Fortunately, we can be warned about such cases by enabling this flag in GHC. If we type again the definition in, we get a warning of this form, which simply says that any possible value combination that is an instance of these two patterns will not be matched by our function foo and will give us back a runtime error. One more example here. What will happen in this case? As you can see here, the two arguments we give to foo are two empty lists, and this perfectly matches the third clause, but it also matches the second clause. Like I told you before, Haskell performs pattern matching always top-down, so we will not get a 3 in this case, but a 2. And not only that, there is no way we'll get a 3 in this case, because all cases covered by the third clause are subsumed by the second clause. So this means that the third clause is actually dead code. Fortunately, we can also be warned about that. By enabling this flag and typing again our definition, we get a warning of this form, which says that the third clause can be safely removed from the match without affecting the semantics of the program at all. Now, well, everything seems rosy, thanks to GADTs, exhaustiveness, and overlapping checker. Yes, it's based on an algorithm designed in 1994 by Maranget for compiling pattern matching, actually. And was adapted, adjusted to work for the warnings. Well, now we come to the problem. In 2006, generalized algebraic data types were introduced in GHC. And since then, things are not so rosy anymore. First of all, what are GADTs? As their name indicates, generalized algebraic data types, generalized normal data types. So for example, here, I've defined vectors that are length index lists. As you can see, I've named the constructors the same way as before. But the difference we have here is that the type constructor vec takes, apart from the type of elements it contains, it also takes a natural number at the level of types, which indicates the length of its vector. So in this sense, nil here returns a vector of length 0, while cons returns a vector, takes an element of type A, a vector of length n, containing elements of type A, and we get a vector of length successor of n. That means n plus 1. In this sense, now we have more precise types, and we can represent parts of the structure of our of our terms in the types. Now we can do all normal stuff with GADTs like we could with ADTs, but we can do even better stuff like this. Here I have function zip that takes two vectors of the same length, which is indicated by the usage of the same type variable n here. And we also have the same n in the result, which means that we ask from the type system actually to prove this property, this important property of zip for us, that the lengths of the input vectors will be the same, and also will be the length of the output vector. Well, the problem is that if we type this in GHC, we get a warning of this form, and it's kind of expected, like we've seen before, because actually these combinations are missing. Well, actually, this here GHC cries wolf because both these combinations are ill-typed. If you recall the definition of vec here, we ask at the signature, we ask that these two variables are the same, but if you check the types of the data constructors, this can never be unified for whatever n we choose, right? So these are both ill-typed. Well, what most of us do in this case is, if GHC is a warning that something is missing, then we put it in ourselves. Well, fortunately, if we type this, I've added here the first vector issued as missing. We get an error, a correct error, that 0 cannot be unified with successor of n. This makes a lot of sense because these two vectors have different lengths. And this is good because it means that our type system is expressive enough and can detect dead code, like the last clause here, statically. Now, but the problem is that what can we do in case we don't add the clauses? We get a warning. If we add them, we get an error. So most of us, what we do, we silence the compiler with a catch-all clause like this, where we say that whatever else doesn't match the first two clauses, well, that's what you'll do. And we know that this case actually covers nothing, because all well-typed combinations of values will be matched by the first two clauses. And unfortunately, we don't get a warning for this. So we have two problems. First of all, we get false alarms regarding exhaustiveness. We get warnings that the function is not exhaustive while it is. And also, if we add clauses of this form, we do not get warnings that some of them are overlapped while we should. Well, the result is that most programmers do not trust the emitted warnings of GHC anymore. I mean, this problem has been up for some years now. And also, most of them use this technique with overlapping, with the overlapping pattern, just to suppress the warning. Even some of them just turn the warnings off. Well, none of this would have happened if we did it my way. Instead of describing it in theory, I'll just show an example, a typical example of this presentation. Well, the general idea is this. Before examining our function, we just consider everything missing, right? If we have no clauses, we cannot handle any possible value combination. So we start, at first everything is missing, which we can represent with two wildcards. And then we inspect the first clause. What happens here? The first clause indicates, it starts with a nil and indicates that we will force the evaluation of the first argument, whatever that is. And if it is a nil, we'll continue and evaluate the second argument to check again if it's a nil here. So the first thing we do is we split this two general wildcard into a cons and a nil, which are the different data constructors we can have for the first argument. Now, as you can see here, although we split this in these two, our first clause starts with a nil, so it cannot possibly match or contribute in covering this case. So all patterns of this form are at this point uncovered. If you consider that we have only the first clause of the match, and someone gives us this as a first argument, we cannot match. Nevertheless, we can contribute in covering this case because we start with a nil. So we do the same thing, and we expand the second wildcard into a cons and a nil because we want to check for equality here. The same reason as before, this case cannot be covered by the first clause, but this is exactly the first clause, so this is fully covered by our clause. Now what we have up to here, we started with an initial set of uncovered cases, values that cannot be handled by our function, and we took into consideration the first clause, and we got what cases does the first clause cover and which are still missing. Now what we do is we repeatedly do this for every clause, and we repeatedly transform this set. Well, at the end, when we have checked all the clauses, we will have information both about which cases are covered by every clause and also which cases are not covered or handled by any of them. Well, let's see the second one. Something important here. You see, by construction, all the vectors we generate to be issued as missing are disjoint, so we can check them separately and then just get the union of the results to get back a final result. For example, here we have a mismatch. The second clause starts with a constant. Here we have a nil, so this remains uncovered. We did the same thing as before, right? Here we both start with a cons, so we match the first argument, and we split the second argument into a nil and a cons. This remains uncovered because we have a mismatch, and this is fully covered. So our figure looks like this. Now, yes, I don't think I have to step through this. Obviously, the last clause covers everything. We check them separately. We match the first, we match the second, so both of them are covered. And our situation looks like this. Well, the inputs of our algorithm was just the clauses, the three clauses, and the output is both the covered cases, here with green, and the orange cases, not the intermediate ones, just the final ones that represent all cases that are still uncovered, although we've checked all the matches. Yes, I probably don't know. Sorry for that. Well, now, until this point, everything looks, if we issued warnings right now, we would get the same results as we get right now with GADT. A match is considered total if the final set of uncovered cases is empty. If nothing is missing, then everything is covered, right? Well, what we don't force here is the well-typedness. And what GADT doesn't do is exactly this here. Also, for the redundancy check, to consider a clause useful, it has to cover at least one case. So we need the set of well-typed cases it covers to be non-empty. So now, the second phase of the algorithm performs like this. We have the signature, and we check every clause that our algorithm generated, both covered or uncovered, green and orange boxes. The first one passes the test with n equal to 0. The second one as well, with successor of n for some n. Now, the third one fails, as we said before, because the type checker will try to unify 0 with successor of n, and no such n exists. So these two fail to pass the test, and we end up with a figure like this. Now, this means that the first clause is useful because it covers something. The second is useful as well. Now, here we can see that we can emit a warning about the third clause, which is actually redundant that we knew. But in order to see that, GHC gives us something like this. But in order to see that, we'll have to get the empty set here. And also, we know that it's total because the final set of uncovered cases is also empty. Well, I was quite fast. What I've shown you, yes, I was a bit brief. We briefly saw how pattern matching works in Haskell. I've explained a bit how the basic static checks for pattern matching works, about totality and redundancy. I've explained you how the incremental approach works, which we designed, and it's quite easy, actually. I didn't show it here, I just implied it, that it's really easy to check that a pattern vector is well typed in GHC since we have the existing infrastructure. Well, what I haven't discussed is that we have formalized the algorithm, and also we have a prototype implementation in GHC. We support guards and literals as well, and we reason about laziness. Also, we have formalized this part, not wholly but partially, in our formalization. And also, we have tested our implementation both on GHC. But everything is structured using ADTs, GADTs, and pattern matching, right? So we had plenty of test cases because GHC performs bootstrapping. And also, we've run the test suite, and we seem to perform as expected on every test case. And also, we have, if I remember correctly, 6 or 7 cases where we get even better results. What we plan for the future? Well, we would like to optimize the implementation, both in terms of space and time, because I would like to be a part of GHC 7.10. Also, it would be nice if we could get a case study on the Hackett's libraries, because a lot of them, not only just to check our implementation that works as expected, but also many libraries use GADTs, and cases like the one I showed you before with the overlapping pattern at the end can be detected and now safely removed from all these matches. And so we would like to improve these libraries. Also, what we would like to do in the future is to represent and handle formally and in our implementation more of GHC's syntax extensions like bank patterns, view patterns, pattern synonyms, and so many others. And finally, we would like to have to improve a bit the reasoning for guards, and that could be done by plugging in probably one of these tools and maybe more. Yes, I think this is it. Well, thank you very much.
Plenty of time for questions.
Yeah, I would like to have a lot of them. Actually, I have backup slides. I never expected to finish so soon.
Yeah. You said you have formalized.
Yes.
What do you mean by that?
I've written down the math, and I've sketched a lot of important properties like the disjointness I told about before. Also, of course, termination, and some things about laziness, which I haven't discussed much here. I mean, well, I've formalized the syntax, I mean, all syntactic forms, and the semantics. I mean, it's an ongoing work, but at least the basics are all proved to be working right.
So you have a hand proof that the algorithm is...
Yes. I could do it in copy, yes.
Presumably, it should be possible to optimize the pattern matching code that you generate, given
Yes.
the information you've got, right?
Yes, we could probably propagate this to the compiler. Yes. I am. Actually, we can do this, but I don't think it's it's so important because what we can do is really cheap, is to just remove the overlapping patterns. I mean, if something is really redundant, we can safely remove it and save ourselves some code, right? But about the exhaustiveness, the only thing that we really get from this is that we remove an if then else at the end, right? I mean, if the final case covers everything, then we don't have to produce an else cross, which GHC does if something is non-exhaustive. I mean, if nothing, the above word. But yes, probably we can do that. I mean, we do far more reasoning. Haven't discussed here. We also check which clause covers which case or which cases, and in which order are the arguments forced. So maybe this is more important information that we could propagate probably to the compiler, to the compiling of pattern matching. But yes, it can be done.
Well, there is a different flavour here. So a lot of Luc Marjoy's work was about generating an efficient automaton to do maximally efficient matching. It made it all quite complicated, but it got very good code out of it. Here, your stress is on a kind of fairly intuitive, one equation at a time, propagate the cases that don't match story, which doesn't really lead to an efficient algorithm.
Yes.
It leads to good error messages. So I think the emphases are a bit different. And it's never been very clear to me whether Luc's techniques would make a lot of difference in a lazy language where you more or less have to match in the order specified anyway. So we do match a kind of column at a time, just like every decent compiler does. But I'm not sure we could do much better than that.
I think that this way we can extract more information about the maths.
Can you give an example of an optimization you might get as a result of this?
I told you already the simplest one. We can remove all matches that are useless.
Okay, yes, ones that are entirely redundant, you throw them away. Fine, yeah.
Yes.
Aside from that?
Yes, about the exhaustiveness. I mean, if we know, I wouldn't do it actually, but wait. Here, since we know that the second clause, the third clause is redundant, we can remove it. And in this sense, the function with only the two first clauses, it's total. So in a sense, if we don't match the first clause, we can match the second, right? This is not true, actually, because we have to force the arguments first to see if they are real terms or if they diverge, right? So I don't think that we can get anything useful out of it. I mean, even if we know that there's no other case, it's either the second one or we fail after that because of divergence. We have to force the arguments to check that we won't diverge, right? So I don't think that we get anything useful.
So if you have like an index type with like 5 constructors and only 2 of them apply for that particular value of the index, then you can avoid, once you've tested the first one, then
It must be the other one.
It must be the other one, so you can
yeah.
avoid that test.
Yeah.
If you know that something, for example, we don't have to check the first clause if you mean that. Sorry.
So for example, it would be more better if it was 3 constructors, but not 2. I mean, I don't understand this forcing business that you're talking.
Wait. If we're here, we know that we didn't match the first clause and we're checking the second.
Yeah.
We don't have to force the evaluation of this because we already tried to match with nil.
Correct.
So we can avoid one check, right?
In this case, you don't even need to look at the second argument.
Well, you do, because
No.
the first match may have failed on nil or on the second nil.
No, but if you know the first one is nil, you know that the second one must be nil.
Yeah,
No. Now we're checking the second clause, which means that the checking before
And
failed.
if the first,
But we don't know if it failed here or here.
If the first one's nil, the second one might be bottom.
Right.
okay.
But, it was,
Right, but do you see what I mean? If this was a strict language, then
if it was, yes. All these problems just appear in Haskell, right? Because it's lazy.
Wait, if the first one was nil, the second one cannot be bottom in this case, right? I mean,
Yes, because we would have crossed the
No
first one.
bottom. There's a call.
The way to cross so it, yes. It must have been cons bottom, right? To be here. It might either be cons bottom or cons. We have to check the second argument anyway here. because
You have to evaluate it, you have to check it.
what?
You have to evaluate it, you have to test it.
Yes, this is it. We can't avoid it.
But
Also-
still, it seems that the type system is not really taking into account, as it is before your extensions, it's not taking into account that for general ADTs, certain combinations are simply illegal. And
Well, with ADTs, it's always legal, right?
with generalized ADTs, the fact that only those 2 patterns out of the possible 4 patterns
Yes.
are actually sensible, it seems to be something that maybe could be propagated.
I mean, the type checker does the reasoning, but in GHC, these are 2 separate checks. The issuing of warnings and the compilation itself are different in different phases of compilation. So,
In the tradition of ML-like languages, or Hindley-Miller-like languages, pattern match exhaustiveness was not kind of type directed, and that has remained the story in GHC, and that's not satisfactory when when you introduce index types, and that's what this work is trying to address.
By Peter Sestop, right, where he takes negative information into account and generates more efficient pattern matching. And it seems that might actually fit here, right, that you get maybe other sources of negative information, which might be the type.
Yeah, so if you haven't been able to match on a particular clause, then you know that it's definitely not some type is not int or it's not.
Yes, and you use that in subsequent.
Do you know what that paper was called?
Fabrice is
Something
partial evaluation.
called partial
But I
evaluation.
suspect Méranger's
Yeah, no,
output does the
Fabrice
same.
is
doesn't it?
yeah, it's most of these are in Méranger's or the follow-up
Yeah.
by
Yeah.
Le Faison, yeah, Fabrice and
Yeah.
Méranger. These are all in there, I think.
Yeah.
But and they're all in a camel as well. But it's strict, so you do avoid all.
Yeah, and they don't have GADTs.
Oh, we
No,
do.
we
We
do.
do. We do, and we have this.
The optimization.
Yeah, we have the optimizations based on the exhaustivity on the types as well.
Oh, cool.
I think. I'm
I
not sure.
didn't realise
anything's
that had
written.
gone into. I know GADTs
Yeah.
indeed gone in fairly recently.
Yes, yeah,
But
version
the,
4. Jacques wrote it all in one.
Yeah.
I don't think he wrote anything about it, but it seems
No,
to be.
that's-
It seems to be. It seems to be
Nice.
essentially the same as this algorithm, roughly, except with
yes.
Méranger's thing.
So, well, actually, laziness is quite important here. It's a bit strange that I have this in my backup slides, not the basic ones. With laziness, we get an additional case. Until now, we had useful, redundant, but with laziness, we get something more. Consider this example. It's simple ADT, right? The second clause is considered useless by GHC and by us. But it's not, because if we call it this way, we'll fail to match the first clause because of the false, we'll try to match the second clause, and we'll evaluate the first one, and we'll cross. If we remove it, of course, we have different semantics, and we get a 3, right? So this is an error even with the algorithm I presented you before. I mean, I didn't include the strictness thing. How to call this? Okay. Yes. Now, with GADTs, it becomes even worse. Let's say we have these 2 data types. As you can see, F1 and G1 are indexed by int, while F2 and G2 are indexed by 2 different types, right? If we have a function like this, FAGA, the only reasonable value to give here is F1 and G1. All other possible combinations, F1, G2, F2, G1, and F2, G2 are all ill-typed. Yet, if we add this as a second clause, what does the algorithm give us? It starts with an empty on the first clause, and we get this as missing. And this is the case covered. Given, okay, there's no reason checking this. Now, the thing is here. The first clause seems to cover F1, G1, and the second one covers F2, G1. And these are the uncovered. Both of them are ill-typed. This is also ill-typed. So we get that the match is exhaustive. Nothing remains uncovered. And also the second clause here is redundant because this is ill-typed. But if we remove the second clause because it's redundant, then we get these as missing. The first one is ill-typed, but the second one is well-typed because F2, let's type fcar, and wildcard may have any type, whatever. That was fast, kind of.
So,
My point is that what we get here is that we get that the second clause is redundant and that we are total, but if we remove it, we're not total anymore. Why does this happen? Right? This is inconsistent because what we do here actually to the second clause is that, well, okay, we ignore the first argument, but we know that it's forced, right, by the first clause. And then we force the second one. That's what, as you can see here, the second clause implies the cases where we have F2 G1, right? There's nothing else left with G1 as a second pattern. So, what about the second clause? Is it useful? Is it redundant? Is it what? I mean, my choice here is a bit different. Well, what this does actually, it eliminates this pattern. It doesn't, I mean, it filters out at the bottom at the second argument, which is not forced by the first clause, right? The first clause will force the second argument only if the first one is an F1. In any other case, we won't force the second argument. We'll stop matching the first clause. Well, so we have these cases. A clause may cover some, something I didn't write here. I mean, well-typed everywhere, right? So we may cover some well-typed cases. In this case, we're useful, right? We may cover no cases and not force anything. So in this case, we're totally redundant. We have the third case, which we can really easily detect with my algorithm, because every time we branch here, the structure does not help. G1, how to say this? Just give me a split second. Yes, I didn't solve the intermediate steps. That's the problem. Well, G1 here splits this into F2G1 and F2G2, right? Every time we have a branching, this means that this clause forces something. And we can really easily detect this because we do the branching, right? So in case we have a branching, we issue a different warning of the form like this clause covers no cases, but it forces some evaluation. We don't know what to do with it yet, but I think it's, from a scientific point of view, it's quite interesting to see what's going on. And it's, I mean, it's quite novel because no other language right now has both GADTs and laziness at the same time. And this is the only way this can appear. I wanted to say it.
This function will never return 2, right?
Yes, but the second clause is useful because if we call it with F2 bottom, it will cross. And it's quite different because if we remove the second clause and we call it with F2 bottom, we will cross due to non-exhaustiveness. If we keep the second clause, we will cross due to the evaluation.
Who cares how you crash?
Semantically, they're different, right? It may be an error something, so we get the warning on the screen. But if it's just a loop, we will loop forever. I mean, there are different things, right? That's what I believe. I mean, yes, it's a problem anyway. But I don't know. From a mathematical point of view, it's different.
The first one crashes, the second one loops.
What did you say?
The first one crashes, but the second one loops.
Yes.
Okay. Well,
Semantically, they're different. We model them both with this symbol, but okay.
We wrote a whole paper about this 15 years ago called Semantics of Imprecise Exceptions that specifically is trying to say that maybe we shouldn't care too much about different flavors of bottom if that's going to mess up your optimization strategy.
Well, at this point, we have inconsistent results, though. I mean, we have to do something about it, right? We cannot simply say that it's redundant because we'll do the same as happening right now. The programmer will say, OK, let's remove this. It's redundant. And then he get another warning like, whoa, you're not exhaustive.
Oh, so maybe it really is redundant. What happens if you remove it and you arrange not to give such a warning? Right, because after all, all of the...
Actually, that was Tom's suggestion. He told me that because this is something that appeared just right now, it's novel, it's up to us to make the right design choice. So this is another option, another alternative worth making. Yeah, I think it's a good idea too.
So again, the type system would say that you shouldn't get into the, regardless of how you force things, you are not going to get to any other case than the first one.
So it's never going to return 2, right?
Well, what you can do here is replace the second clause by underscore patterns, and then you have a way of calling f and getting 2.
That's true. Even with our algorithm and the intended semantics. Or if we replace the second one with an f2 underscore, which is the same as underscore underscore in this case, it will still work, and it will get a 2. It's really non-exhaustive. Well, the best thing to do, I think, it would be to bank the second pattern so it will be strict, but it's difficult to detect that.
If there are any more questions? If there aren't, so George and Tom are going to be with us for the rest of this week, I suppose, tomorrow and Friday. So they are somewhere on the 4th floor. If you feel like talking to them, just talk to me or just grab them. Okay, well, thanks very much.